Welcome to this coding walkthrough. In this session, we'll explore LeetCode problem number 1399, Count Largest Group. This problem is an excellent practice for mastering concepts like digit sums and grouping numbers efficiently. Let's dive in. In this problem, you are given an integer n, and your task is to group all numbers from 1 to n based on the sum of their digits. Once the numbers are grouped, you need to determine the size of the largest group and return how many groups have that size. For example, if there are multiple groups that share the same largest size, your output will be the count of those groups. The input is a single integer n, where n can range from 1 to 10,000. The output is a single integer representing the number of groups with the largest size. Let's take a look at an example to better understand this problem. If n equals 13, the output is 4. We'll explore why in the next section. To understand the example where n is 13, let's see how the numbers are grouped based on the sum of their digits. For instance, the numbers 1 and 10 both have a digit sum of 1, so they form one group. Similarly, the numbers 2 and 11 both have a digit sum of 2, forming another group. This process continues, with numbers like 3 and 12 grouped together under the sum of 3, and 4 and 13 grouped under the sum of 4. The remaining numbers, such as 5, 6, 7, 8, and 9, each form their own groups since their sums are unique. The largest group size here is 2, and there are exactly 4 groups with this size, the groups for sums 1, 2, 3, and 4, therefore, the output is 4. Another example is when n equals 2. Here, the numbers 1 and 2 each form their own group, both of size 1. Since the largest group size is 1 and there are 2 such groups, the output is 2. Now let's examine a more detailed example where n equals 24. The numbers from 1 to 24 are grouped based on their digit sums. For instance, all numbers where the sum of their digits equals 6, such as 6, 15, and 24, form one group. Through this grouping process, we find that the largest group size is 3, and there are 5 groups of this size. This means there are 5 distinct digit sums that each correspond to a group of 3 numbers. Therefore, the output for n equals 24 is 5. The process of grouping numbers based on their digit sums and counting the largest groups remains consistent, regardless of the size of n. The problem comes with several constraints and edge cases to consider. First, n is guaranteed to be between 1 and 10,000, so the solution must handle both very small and very large inputs efficiently. For instance, when n equals 1, there is only one group with one number, so the output is always 1. On the other hand, a large n like 10,000 requires an efficient way to compute and group digit sums. Another important case is when every number forms its own group, such as when n equals 9, resulting in the output being equal to n. Finally, when multiple numbers share the same digit sum, groups are formed, and the output depends on the frequency of the largest group size. To solve this problem, we iterate through all numbers from 1 to n, calculate the digit sum for each number, and use a dictionary to track the frequency of each sum. After identifying the maximum group size, we count how many groups have that size and return the result. To solve this problem, one possible approach is to use a brute force method. The idea is simple: we group numbers from 1 to n based on the sum of their digits. To do this, we iterate through all numbers from 1 to n, calculate the sum of the digits for each number, and use a dictionary to group numbers by their digit sums. In this dictionary, the keys represent the digit sums, and the values represent the count of numbers with that sum. Once the grouping is complete, we can determine the size of the largest group and count how many groups have this size. While straightforward and easy to implement, this approach involves repeatedly calculating the sum of digits for each number, which takes time proportional to the number of digits in the number. For n numbers, this results in an overall time complexity of roughly n asterisk log n, where log en accounts for the digit sum computation for each number. Now, let's consider an optimized approach to improve the efficiency of the solution. The main focus here is to eliminate redundant calculations and streamline the digit sum computation. One efficient way to calculate the digit sum is by extracting the last digit of the number using the modulus operator and then dividing the number by 10. This process is repeated iteratively until the number is reduced to 0. Using this method, we can compute digit sums in a single pass through the numbers from 1 to n. The frequency of each digit sum is stored in a dictionary, and once all numbers are processed, we can determine the largest group size and count of such groups in a single traversal of the dictionary. This approach minimizes data storage requirements and leverages efficient digit sum computation, achieving a time complexity of O n asterisk log n. The space complexity is O k, where k is the number of unique digit sums, which is typically small compared to n. The chosen strategy for this problem builds upon some key observations. One important realization is that the range of possible digit sums is inherently limited. For instance, the maximum digit sum for a number like 9999 is 36, achieved by summing its digits, 9 plus 9 plus 9 plus 9. This means the number of groups we need to consider is restricted and does not scale with n. This bounded range allows us to use a compact structure, like a dictionary or even an array, to group numbers by their digit sums. Moreover, the sequential nature of processing numbers from 1 to n ensures that the problem is linear in essence, and the optimization lies in how efficiently we calculate digit sums while avoiding unnecessary operations. This approach is chosen because it strikes a balance between clarity and performance. It avoids overcomplicating the solution while still improving practical efficiency. Although the time complexity remains O n asterisk log n, the optimized operations make it more suitable for handling larger values of n. When considering trade-offs and alternatives, the brute force method, while easy to implement, does not take advantage of the bounded nature of digit sums, leading to less efficient performance. The optimized approach, on the other hand, achieves the same theoretical time complexity but is more practical for larger input sizes due to reduced overhead and streamlined operations. Another alternative could involve using an array instead of a dictionary to store digit sum groupings, which might save memory in some cases. However, dictionaries are generally more intuitive and flexible for this type of problem, especially given the sparse distribution of digit sums. Finally, in terms of complexity, the time complexity remains O n asterisk log n, driven by the digit sum computation for each number, while the space complexity is O k, where k represents the unique digit sums. Since k is typically small, the approach is efficient and well-suited to the problem's constraints. In this problem, we are tasked with grouping numbers between 1 and a given number n based on the sum of their digits, and then determining the size of the largest group. For instance, when n equals 13, we calculate the digit sum for each number. Numbers like 1 and 10 both have a digit sum of 1, while numbers like 2 and 11 both have a digit sum of 2, and so on. This process results in groups such as 1, 10, 2, 11, 3, 12, and 4, 13, each corresponding to a distinct sum of digits. Among these, all groups have a size of 2, making 2 the size of the largest group. To achieve this, we'll first process the input to ensure it's valid, then iterate through numbers from 1 to n, calculating the digit sum for each number. Let's now understand how this iteration and grouping process works. To compute the sum of a number's digits, we use modulo and integer division operations. By repeatedly extracting the last digit with the modulo operator and removing it with integer division, we can efficiently calculate the digit sum. Once we have the digit sum for a number, we store it in a dictionary. The dictionary maps each digit sum to the numbers that produce it. For example, if n equals 13, the dictionary would look like this: 1, 1, 10, 2, 2, 11, 3, 3, 12, 4, 4, 13. However, instead of storing full lists of numbers, we can simplify and optimize the dictionary to store only the count of numbers for each digit sum. This changes our example dictionary to 1, 2, 2, 2, 3, 2, 4, 2, where the values represent the frequency of each digit sum. This approach reduces memory usage while still allowing us to calculate the largest group size. With the dictionary now representing the count of numbers for each digit sum, the next step is to identify the largest group. To do this, we find the maximum value among the dictionary's values, as this represents the size of the largest group. For example, in the case of n equals 13, all digit sums occur twice, so the largest group size is 2. While implementing this algorithm, it's important to consider edge cases. For small values of n, such as n equals 1, there's only one group, and its size is 1. For large values of n, the algorithm must remain efficient. We also need to ensure correctness for multi-digit numbers, such as when n equals 1000. Efficient digit sum calculation and memory usage optimization are key to handling these scenarios effectively. One of the most important insights here is that the digit sum calculation can be performed efficiently using mathematical operations like modulo and integer division, avoiding the overhead of converting numbers to strings. By using a dictionary to track the frequency of each digit sum, we enable quick updates and lookups as we iterate through the numbers. Storing only the counts, instead of full lists of numbers, significantly reduces memory usage. In terms of efficiency, the algorithm runs in O, n*d, time, where n is the range of numbers and d is the number of digits in each number. This is because we calculate the digit sum for each number. Space complexity is O, k, where k is the number of unique digit sums, which is typically much smaller than n. Further optimizations, like stopping early if the largest group size is determined or pre-computing digit sums, can improve performance for very large inputs. To implement this algorithm, we begin by initializing a dictionary to store the frequency of each digit sum. We then iterate through numbers from 1 to n. For each number, we calculate its digit sum by repeatedly extracting and removing the last digit using modulo and integer division. Once the digit sum is calculated, we update the dictionary to increment the count for that sum. After processing all numbers, we find the largest group size by taking the maximum value in the dictionary. This approach ensures that we efficiently calculate the desired result while optimizing memory usage. The algorithm is both simple and scalable, making it well suited for a range of inputs, from small values of n to very large ones. This solution to LeetCode problem number 1399 count largest group uses a dictionary to group numbers from 1 to n based on the sum of their digits. Here's a detailed explanation of the code. 1. Imports *. We import default dict from Python's collections module. This allows us to initialize dictionary values to 0 without explicitly checking if a key exists. 2. Function definition *. The function count largest group takes an integer n as input, where n is the upper limit of the range of numbers we are analyzing. 3. Digit sum groups *. We initialize a default dict called digit_sum_groups with int as the default factory. This will automatically initialize missing keys with a value of 0. 4. Calculate digit sums *. We loop through each number from 1 to n. For each number, we calculate the sum of its digits. This is done using a generator expression inside sum, which converts the number to a string, iterates over each character, converts it back to an integer, and sums them. 5. Group numbers by digit sum *. For each calculated digit sum, we increment the corresponding value in the dictionary. This effectively groups numbers by their digit sum and counts how many numbers are in each group. 6. Find largest group size *. After the loop, we find the largest group size by taking the maximum value in the digit_sum_groups dictionary. This gives the size of the most populous group. 7. Count largest groups *. Next, we count how many groups have this maximum size. We do this by iterating through the dictionary values and summing up the number of entries that match max_group_size. 8. Return result *. Finally, we return the count of the largest groups. This is the required output of the function. The code is efficient with a time complexity of approximately O, n*d, where d is the number of digits in the largest number, and it uses space proportional to the number of unique digit sums. It handles edge cases like n equals 1, single number, correctly, as there's only one group in that case. Here, we start by importing the necessary Java utilities and defining our solution class. The main method, countLargestGroup, takes an integer n as input and calculates the number of groups with the largest size. To achieve this, we use a hash map called digitSumGroups, where the key represents the sum of the digits of a number, and the value represents how many numbers share that same digit sum. We then iterate from 1 to n, calculating the digit sum for each number using the helper method getDigitSum. For each digit sum, we update its frequency in the map using the getOrDefault method. Once we've populated the map, we use collections.max to find the largest group size by looking at the maximum value in the map. Finally, we loop through the map values to count how many groups match this maximum size, and we return that count as the result. The helper method getDigitSum is a private method that computes the sum of the digits of a given number. It initializes a sum variable to 0 and performs a while loop as long as the number is greater than 0. Inside the loop, we repeatedly extract the last digit of the number using the modulus operator, add it to the sum, and then remove the last digit by dividing the number by 10. This process continues until there are no more digits left. Once the loop completes, the method returns the total sum of the digits. This utility function is essential for breaking down numbers into their digit sums, which is the basis for grouping them in the main count_largest_group method. To solve this problem, we start by initializing the digit_sum_groups dictionary as a default dict with int as the default value. This allows us to add entries dynamically without needing to manually initialize keys. Next, we iterate through all the numbers from 1 to 13, calculating the digit sum for each number. For example, the digit sum of 1 is simply 1, so we increment the count for the key 1 in the dictionary. Similarly, for 2, the digit sum is 2, and we increment the count for key 2. We continue this process for numbers up to 9, where each digit sum corresponds to the number itself, so the dictionary grows to have keys from 1 to 9, each with a count of 1. When we process numbers with multiple digits, such as 10, the digit sum is 1 plus 0, which is 1. This increases the count for the key 1 in the dictionary to 2. Similarly, for 11, the digit sum is 1 plus 1, which is 2, so the count for key 2 also becomes 2. By the time we finish processing all numbers up to 13, the dictionary reflects the frequency of each digit sum, with some keys having counts greater than 1 because their digit sums are repeated. After populating the digit_sum_groups dictionary, we move to determine the largest group size. To do this, we look at the values of the dictionary, which are the counts of each digit sum. In this example, the values are 2, 2, 2, 2, 1, 1, 1, 1, 1. The maximum value among these is 2, which means the largest group size is 2. The next step is to count how many groups have this maximum size. We identify the keys corresponding to this size, which are 1, 2, 3, and 4, as they all have a count of 2. Therefore, the total count of groups with the largest size is 4. Finally, the output for this example is 4, indicating there are 4 groups with the largest size. Now, let's consider a larger example where n is 24. As before, we initialize the digit_sum_groups dictionary as an empty default dict with int as the default value. Then, we process each number from 1 to 24 to compute their digit sums. For numbers 1 through 9, the digit sums are simply the numbers themselves, so the dictionary gets keys from 1 to 9, each with a count of 1. For numbers 10 through 19, their digit sums repeat as 1, 2, 3, and so on, up to 9 again. For example, the digit sum of 10 is 1, 11 is 2, and so forth. Finally, for numbers 20 through 24, their digit sums are 2, 3, 4, 5, and 6 respectively. After processing all numbers, the dictionary captures the frequency of each digit sum. The final state of the dictionary is 1, 2, 2, 3, 3, 3, 4, 3, 5, 2, 6, 2, 7, 1, 8, 1, 9, 1. From here, we observe that the maximum group size is 3, as the largest count among the values is 3. To complete this example, we count the number of groups that have the maximum size of 3. Looking at the dictionary, the keys with a count of 3 are 2, 3, and 4. This means there are 3 groups with the largest size. Therefore, the final output for this example is 3. Lastly, let's briefly consider the simplest case where n is 1. In this case, the only number is 1, so the digit sum is also 1. The digit_sum_groups dictionary ends up with a single entry, 1, 1. The largest group size is 1, and there is only one group of this size. Thus, the output for this case is 1. The time complexity of our solution can be broken down into distinct parts. First, we have the digit sum calculation. For each number from 1 to n, we compute the sum of its digits. This involves converting the number to a string, iterating through its digits, converting each digit back to an integer, and summing them. Since the number of digits in a number is proportional to the logarithm of the number base 10, or log 10 of the number, the time for a single digit sum computation is O log 10 number. When we consider all numbers from 1 to n, the total time for digit sum calculations becomes the sum of log 10, 1, plus log 10, 2, plus log 10, n. This simplifies to O n asterisk log 10 n because the sum of logarithms grows proportionally to n times log 10 n. Next, we group numbers by their digit sums. For each number, we update the count of its digit sum in a dictionary. Since dictionary operations like insertion and lookup take constant time on average, this step runs in O n. Now, let's look at how we find the largest group size. We iterate through the dictionary values to determine the maximum size of any group. The maximum number of unique digit sums in our dictionary is limited by the largest possible sum of digits, which is bounded by 9 times log 10 n. Because this number of unique digit sums is very small compared to n, the step is effectively constant time, or O1, with respect to n. Similarly, counting the groups that have the maximum size involves another iteration through these dictionary values. Since the number of unique digit sums remains bounded, this step is also O1. When we combine all these steps, the digit sum computation dominates the overall time complexity. Therefore, the total time complexity for the solution is O n asterisk log 10 n. Next, let's analyze the space complexity of the solution. The main contributor to space usage is the dictionary, called digit_sum_groups, which stores the frequency of each digit sum. The number of unique digit sums is limited by the maximum possible sum of digits, which is bounded by 9 times log 10 n. As a result, the space required for this dictionary is O log 10 n. Additionally, there is temporary space used during the digit sum computation. Converting a number to a string and iterating through its digits requires space proportional to the number of digits in the number, which is O log 10 n. However, since this temporary space is reused for each number, it does not add to the overall space complexity. Combining these factors, the total space complexity is O log 10 n. Let's compare this approach to a naive solution. A naive method might involve manually checking every pair of numbers to group them based on their digit sums, which would require a time complexity of O n squared. In contrast, the optimized solution avoids redundant comparisons by grouping numbers based on their digit sums in a single pass. This leads to a significantly better time complexity of O n asterisk log 10 n and space complexity of O log 10 n. Regarding the different cases, the time complexity remains consistent across the best, average, and worst cases. This is because the number of iterations and the cost of digit sum computation depend only on n and the number of digits in the numbers, which do not vary. Similarly, the space complexity remains O log 10 n in all cases since it is determined by the size of the dictionary storing the digit sums. Finally, let's briefly justify the big O notation used in this analysis. For time complexity, the digit sum computation for each number takes O log 10 number time. Summing this cost across all numbers from 1 to n gives O log 10 1 plus log 10 2 plus log 10 n, which simplifies to O n asterisk log 10 n. For space complexity, the dictionary size is determined by the maximum digit sum, which is bounded by O log 10 n. Taken together, these calculations confirm that the time complexity is O n asterisk log 10 n, and the space complexity is O log 10 n. One common mistake when solving this problem is miscomputing the digit sum. For instance, some people treat the number as a string, but then forget to convert the characters back to integers before summing them up. This leads to incorrect group assignments, which ultimately affects the final result. To prevent this, you can use a reliable formula, such as summing the digits with sum int d for d in str number in Python. Another frequent error is overlooking edge cases. For example, testing only with mid-range values and ignoring small inputs like n equals 1 or large constraints like n equals 10⁴. Missing these could result in runtime errors or incorrect outputs. Including both small and large edge cases in your test plan ensures robustness. Finally, inefficient implementations can also cause problems, especially for large values of n. Using nested loops or redundant calculations increases time complexity and may result in time limit exceeded errors. Instead, focus on optimizing your solution by pre-computing digit sums where possible, and leveraging a hash map for grouping numbers efficiently. Another common issue is incorrectly initializing data structures. For example, using a list instead of a dictionary or failing to properly initialize counts can lead to unexpected behavior, such as key error when accessing non-existent keys. To avoid this, use a dictionary to group numbers by their digit sums and ensure it is initialized correctly. Additionally, misunderstanding the problem's goal can lead to incorrect outputs. Some mistakenly return the largest digit sum itself instead of the size of the largest group. This happens when the problem statement isn't fully understood. To fix this, always ensure you carefully read and comprehend what the problem is asking for. Here, it's the size of the largest group, not the digit sum. These kinds of mistakes highlight the importance of both correct data structure usage and a clear understanding of the problem requirements. In interviews, it's crucial to address edge cases explicitly, such as n equals 1 or n equals 10⁻4. Interviewers often include these scenarios to evaluate your ability to handle boundary conditions effectively. Make sure to articulate your approach clearly, especially when using a hash map to group numbers. For example, explain how you compute the digit sum and why it helps reduce complexity. Interviewers also appreciate discussions of trade-offs. While a brute force approach might be easier to implement, you should be able to explain why a pre-computation-based solution is more efficient for large inputs. Lastly, highlight any spacetime trade-offs in your solution. For instance, a dictionary-based approach might use O(n) space, but it improves readability and performance compared to using nested loops. These insights demonstrate both your technical depth and your ability to communicate your thought process effectively. This problem is closely related to others on LeetCode that involve digit sum calculations or grouping based on derived properties. For example, LeetCode 1399, the problem we're solving, groups numbers by their digit sums. LeetCode 1085 focuses specifically on digit sum calculations, while LeetCode 258 deals with repeated digit sum operations, emphasizing the same core concept. Additionally, LeetCode 1170 compares strings based on a derived frequency measure, which is conceptually similar to grouping numbers by their digit sums. When it comes to alternative approaches, a brute force method involves calculating digit sums for all numbers, grouping them, and finding the largest group size. While this is simple, it's inefficient for large n because its time complexity grows with O(n*k), where k is the average number of digits in n. A more optimized approach uses a hash map to store digit sum counts, which eliminates redundant computations. This sacrifices slightly more space but is significantly faster for large inputs. Another efficient strategy is pre-computation. By pre-computing all possible digit sums for numbers up to n, you can reuse these values during the main computation. This approach reduces runtime, especially for scenarios with multiple queries, as you're no longer recalculating digit sums repeatedly. The trade-off here is the additional memory required to store the pre-computed values, but this is often a worthwhile exchange for the improved efficiency. Pre-computation is particularly valuable in competitive programming or real-time applications where reducing runtime is critical. By combining pre-computation with a hash map-based grouping strategy, you can achieve a highly optimized solution that balances both speed and readability. Great job working through this problem. To summarize, we used a hash map to group numbers by their digit sums and identified the largest group size efficiently. This approach reinforced the importance of managing complexity and leveraging data structures effectively. Thanks for watching, and don't forget to like, share, and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!